Welcome to the second segment of the 8th lecture for the online series of lectures on the course of Introduction to Category Theory. In the last segment, we discussed about graphs. We went over the definition of a graph along with an example of how to construct the product of two graphs. In this segment, we will start discussions with the graph homomorphism. Okay? So, let me go to the discussion of graph homomorphism. Okay? So, a graph, as we have told already, that it's a quadruple consisting of the following data: V, A, S or C, P, G, T. These are two maps and these are two sets. Involves two sets and two functions. Okay. Now, what does it mean for two graphs to be comparable to each other? For two graphs to be comparable, their two sets and their two functions, their two sets and their two functions should be appropriately comparable. So this is a very precise notion of what we have put down here inside the inverted commas. Appropriately. We need to understand what it means by this appropriately. Okay? And for which we have the following definition. Definition of graph homomorphism. Let G, V, S or C, P, G, T is a graph, and we have another graph. So for graph homomorphism, we need two graphs. So the other graph is given by V prime, A prime, S or C prime, P, G, T prime. V graphs. Okay, a graph homomorphism from G to G prime to G prime denoted by f from G to G prime consists of two functions. One function is for the vertices from V to V prime, which we denote by f sub 0. Okay? And another function is between arrows of the corresponding graphs, which we denote by f x sub 1 from A to A prime. So this F, the graph homomorphism between these two graphs, consists of two functions, one between the vertices, the other one between the arrows, such that the two diagrams below commute. The two diagrams below commute. Okay. What are the two diagrams? So let me draw these two diagrams, one on the left and one on the right. A is the set of arrows of graph G, and A prime is a set of arrows of graph G prime. And we know that there is this map F1 from A to A prime. Okay. And there is this set of vertices V of the graph G, and there is this set of vertices V prime of graph G prime. And we know that there is this arrow from V to V prime denoted by F0. Okay. And there is this source map SRC that takes A to V, SRC, and there is this source map SRC prime that takes A prime to V prime. We want this diagram to be used. Okay? Alright. Now to the right, there is another map from, it's a similar type, the vertices are going to be the same. So A prime, B prime, A to A prime is the map F1, and B to B prime is the map F0. Now, instead of the source map, we have the target map, EGT and EGT prime. We want these two diagrams to commute. I mean that we want both of these diagrams to be commutative, okay? And if this is the case, then this F is called a graph homomorphism between these two graphs, G and G prime. So this is the definition. So if you think a little deeply, then you see that under this graph homomorphism, the arrows are bound to their vertices, okay? So under the action of this graph homomorphism, the arrows will not behave differently. They will be bound to their original vertices. Or, under the map of those vertices, so the vertices of V will be mapped to the vertices, so the vertices of G will be mapped to the vertices of G prime, but they will behave in a consistent way. Okay? So they will be bound to their vertices. Okay, now I'll give you examples by means of which you will be able to understand how this is happening. Okay, so we'll give examples of a mapping from a graph to another graph, which is not a graph homomorphism, and then we'll give an example which actually satisfies these properties and becomes a graph homomorphism. Okay. So, all right. So, examples. Below is a mapping between two graphs, that does not respect the condition provided and hence cannot be treated, and hence can be treated as a graph homomorphism. Okay? I need to change the marker. Okay. So what's the example? So I need a colored marker. For this example. So let me draw two boxes first. This is one box containing one graph. On the right there is another box containing another graph. Okay. Alright. So just two vertices on the left graph. This is one. And this is the other vertex of the first graph, labeled by 2. And there is an arrow between them that we draw in black color, and which we label by A. So this is the first graph. And there is another graph on the right labeled by 1 prime. One vertex is 1 prime. So there are 3 vertices here. 2 prime. And there is another vertex, a big vertex, which is 3 prime. And there is this arrow 8 prime from 2 prime to 3 prime. Right? So, we're drawing a map. So, this is a map from one graph to another graph, where the vertex 1 is mapped to 1 prime. How do you see this mapping? Because they have the same color. 1 and 1 prime has the same. They have the same color. So 1 is mapped to 1 prime. So 2 and 2 prime have the same color. So 2 is mapped to 2 prime. Okay. And we have a mapping of arrows as well. 8 is mapped to 8 prime. So we see that it's not a graph homomorphism. Why? So in other words, we have our own notations of F0 and F1. These two maps, F1 and F0. So using these notations, F0 acting on 1, okay, is 1 prime. F0 is a map from the set of vertices V to the set of vertices V prime. V, well, you see that V is just 1 and 2, and V prime is 1 prime, 2 prime, and 3 prime. Okay. So F01 is simply 1 prime, and F02 is 2 prime, and that's it. 3 prime does not have a pre-image since it's not surjective. It's not taken to be surjective. Okay? So now what we conclude, I don't want to erase these 2 diagrams actually. Right? So let me read these 2 diagrams. See if we can have enough space to continue. None of the 2 diagrams, none of these 2 diagrams for graph homomorphism. For graph homomorphism, we need these 2 diagrams to commute separately. Okay? None of these 2 diagrams for graph homomorphism commute for the mapping between the 2 graphs above. Okay. For example, take for example A is in A prime, okay? Sorry, A is in A. Okay. Wait. So, let me write it as this: G equal to B A SRC PGT, and G prime is equal to V prime A prime SRC prime PGT prime. Okay. What else? So V is given by 1, 2, these 2 element set, and V prime is given by this 3 element set. And what else? We have A to be equal to a singleton A, and A prime is also a singleton A prime. Okay. And also observe that if one of A is A prime, okay? Right? Which is in A prime. Now, one has SRC prime composed with, this is what we are doing, SRC prime composed with F1 acting on A, okay? So this this is a map from A to V prime via this path. Okay? And S or C prime composed with F1 acting on A. What is it? F1A is A prime and the source of A prime is 2 prime. Right? While this way, F sub 0 composed with SRC acting on the same arrow A is equal to F sub O. What is source of A? Source of A is 1. And we know that F sub O acting on 1 is 1 prime. So what did we find? Therefore, we found that SRC prime composed with F1 is not equal to F sub 0 composed with SRC. In other words, this diagram does not commute. Okay? Alright. For the right hand side diagram, observe that this diagram. Now observe that for the right hand diagram, so we're going to go to A, from A to V prime via this path. So this is TGT prime composed with F1, right? And that this is going to act on A. There is a single element in this set A. So this is going to be TGT prime. What is F1A? Well, F1A is simply A prime. So TGT prime A prime, target of A prime here is equal to 3 prime. Okay. So now this path, consider this path, and that is given by F0 composed with TGT acting on the same arrow A. What is the target of this arrow A is 2, right? What is F sub 0 acting on 2 is 2 prime. Again, we found them to be unequal, right? So the right hand side diagram does not commute either. Therefore, we have seen that TGT prime composed with F1 is not equal to F0 composed with TGT. Right? We have also seen this, resulting in the fact that the underlying map is not a group, is not a graph homomorphism. Okay, so this was an example of a map which is not a graph homomorphism. Okay, now I'll give you an example of a graph homomorphism. Okay, so let me erase everything. An example of a graph homomorphism. I'll give you an example of a graph homomorphism. So again, we have two graphs. Okay. So let G equal to V comma A comma SRC comma TGT and G prime V prime A prime SRC prime TGT prime be the graphs drawn to the left and right, drawn to the left and right, respectively below. Okay, again we have two boxes here. One box, and there is another box here. So now we have to use markers with different colors again. So there is a vertex. Here, drawn red, labeled by 1, and there is another vertex of the same color, 3. There is a blue vertex, green vertex, 2. And there are 2 blue vertices, 5 and 6. 6. So these are the 2 blue vertices, and there is a black vertex labeled as 4. Black vertex labeled as 4. Okay. So there are 6 vertices altogether, and let me draw the arrows for the graph G. From 1 to 2, the arrow is labeled as A, and from 2 to 3, the arrow is labeled as B. From 5 to 6, the arrow is labeled as E, and there are 2 arrows from 1 to 4. One is labeled C and the other one is labeled D. Okay. Now on the right hand side, this is the graph G. On the right hand side is the graph G prime, for which there is a red arrow labeled 1 prime, and there is a vertex, the red vertex labeled 1 prime, and there is a blue vertex labeled 2 prime. Sorry, not blue, green vertex labeled 2 prime. Okay. And there is one blue vertex called 5 prime, and there is one black vertex called 4 prime. So now there is a loop beginning and ending at 5 prime called Z. There are 2 arrows here, one from 1 prime to 2 prime called W, and another from 2 prime to 1 prime back to 1 prime called X. And there is one arrow from 1 prime to 4 prime called Y. Okay. So now the graph homomorphism is given by the following maps of vertices. I'm just writing down how the vertices are mapped from one graph to another. One is mapped to 1 prime. Why? Because 1 and 1 prime have the same color, and 2 is mapped to 2 prime because 2 and 2 prime have the same color. 3 is mapped to 1 prime again because 3 and 1 prime are both of red color. So 3 is mapped to 1 prime, okay, and 4 is mapped to 4 prime because they are both of black color. 4 is mapped to 4 prime. 5 is mapped to 5 prime because they are both of blue color. And 6 is again mapped to 5 prime because they are both of blue color. Okay, so this is the map between these two graphs. Now we got to check that it's indeed a graph homomorphism. Okay, so we stick to black marker. So let me write down what the color does here. The colors indicate our choice of function, indicate our choice of function f0 from b to b prime, b to b prime, and the conditions for graph homomorphism. You remember that the two commutative diagrams we had before, those were the conditions for the mapping to be a graph homomorphism. The conditions for graph homomorphism given by the two commutative diagrams determine a unique choice of graph homomorphism. Determine a unique choice of unique choice of graph homomorphism that we have drawn here exactly. Okay? The graph homomorphism denoted by f from G to G prime. Okay? This is the unique graph homomorphism that we have for these two graphs. Okay? So now let's check the following things. Okay? There are certain things to be checked. First thing to check about this this arrow f1. Now the function f1 from the two sets, from one set of arrows to another set of arrows. So check that f1 from the set of arrows A to the set of arrows A prime is given by, under this unique graph homomorphism, is given by, well, f1a is equal to W. So under this graph homomorphism, it is mapped to W. Okay? And f1b is mapped to, sorry, B is mapped to X. B is mapped to X. This B guy is mapped to the X guy. F1C and F1D are both equal to F1, so C and D are both mapped to Y. And E is mapped to Z. F1E is equal to Z. So this is the unique graph homomorphism that we have in this case. Okay. Now let's check that under this choice of this function f1 from A to A prime, we indeed have a graph homomorphism, meaning that we have these two conditions of the commutativity of the two diagrams fulfilled. Okay, so let's check. Okay. So what did we really need to check? Let me draw the two diagrams here. We had A prime and V prime, and there was a source map, and there is SRC prime, and that was F1, and this is F0, right? And the other commutative diagram was as follows, with the same vertices A prime, V prime, F1 and F0, but now the source maps are replaced with the target maps TGT and TGT prime. Okay. All right. Now let's see that what is SRC prime composed with F1. Okay. Acting on E, say acting on E. So what we are doing is we are going from A to V prime via this path. So that is SRC prime composed with F1, and that guy acts on an element of A, which is E. Okay. So A here is this A, B, C, D. It's a 5-element set, right? C, D, E, and A prime here is this 4-element set, right? W, X, Y, and Z. So now it acts on an element of A. Where is A? E. E is an element of A. So if this guy acts on E, and which is what? Is F1 of E by definition. I mean that we're claiming that this is the only possible graph homomorphism. So F1E is given by Z. So F1E is Z. So SRC prime Z is equal to 5 prime. And what is now we need to go from A to V prime via this path, and which is what? F sub 0 composed with SRC acting on E is equal to F sub 0. What is SRC E? The source of this arrow E is 5, so F0 5, right? So 5 is mapped to 5 prime, right? 5 is mapped to 5 prime. In other words, 5 and 5 prime have the same color, so they are the same. So you can check for other arrows of A, they will be equal, meaning that this diagram will commute for any choice of elements of A. Okay, this path and that path will give you the same answer. Okay. Now for the target map, this diagram is going to be satisfied. This diagram will also be commutative, and we can check it by using the same arrow E here. TGT prime composed with F1 acting on E is equal to what? So we are going to from A to V prime via this path, so that TGT prime composed with F1 acting on E is equal to TGT prime. What is F1 of E? F1 of E Z. So TGT prime Z is equal to 5 prime because Z is a loop. Okay, and what about the other path? F0, F sub 0 composed with TGT. TGT acting on E is equal to, what is TGT-E? Well, target of this map E is 6. Okay. So what is F0 of 6? F0 of 6 is 5 prime. So they are the same. So now you can check that for any choice of element from this set, you are going to have them to be equal, right? Meaning that TGT prime composed with F1 will be equal to FO composed with TGT for any choice of elements of A. In other words, this diagram will also commute. Okay, this way you check that this mapping is indeed a graph homomorphism. Okay, so that was graph homomorphism. So we end this session with graph homomorphism. In the next segment, we'll start discussions on paths in a graph. Thank you.